Hey, welcome back. This is our second lecture in the Energy 101 Energy and Sustainability course. This is Lonnie Gamble, and we're going to be talking today about energy flows on the Earth, and their relation to sustainability. First, before we get started, I wanted to bring out one more point about energy that's, again, one of these kind of mysterious and unique characteristics of energy. And that's the concept of substitutability. It's used in economics a lot. In economics, typical conventional neoclassical economists will say, well, sustainability isn't a big deal because there's substitutability. Humans are really clever, and if we run out of one material, we'll find a substitute, another substitute. And they say if we run out of energy, we'll find something else. If we run out of one form of energy, we'll find another. And they're right to some extent in that we can substitute one form of energy for another, but again, we need to be careful to take into account the energy quality, the entropy, the orderliness of that energy. But because of the concept of entropy, because we've got to continually offset this tendency for energy to disperse, we've got to offset that and become less useful, that it disperses and becomes less useful, and we have to offset that tendency by bringing in a new source of energy. Remember, we can't really recycle energy. We have to, it flows from a high quality source to a low quality sink. So there is really nothing that we can substitute for energy itself. Energy has no substitute. So that's an important point for sustainability. It's that whole argument that we don't need to be concerned about it, because we do have to have energy to create order and structure, to create something for future generations that we don't leave completely stuck with a world that is going towards entropy. So no matter how clever we get, we'll never find a substitute for energy itself. Another concept I want to bring up from the previous lecture before we get into this whole discussion about energy flows on the Earth is the concept of a stock versus a flow energy source. So a stock energy source is something that it's like a bank account. It's something that there's a certain amount of it sitting there, and as you take it out, you lose it, and it dissipates. So if you have a bank account and you just keep taking money out, $10 a week, $20 a week, if you don't put anything else back in, it's eventually going to be dissipated. It's gonna be gone. And so there are stock energy sources and stock kinds of resources, things, and there are long-term ones like oil and coal and things like that. And there are things that are stocks, but they're renewable stocks, things like forestry and flowing water and things like that. And then there are flow sources of energy. And the flow sources of energy all come from contemporary sunlight. Sunlight is the main source of flow energy. So what we need to do is we need to get away from using the stock energy. It's kind of like using up your bank account, and then get into the use of the flow energy, which is like just using the interest from that account, just using what comes in from the sun. It's sort of like a huge amount of interest we get every day on an account that we didn't have to earn. We didn't really earn the right to have sunlight. It's something that's just given as a gift to by nature to every being on the planet. And so I wanted to point out this difference between stock and flow. You'll see that often in literature if you happen to read other things about energy. So energy flows on the Earth. Let me just list a few: wind, waves, ocean currents, storms, tides. All of these are caused by solar energy, with the exception of tides, which is caused by the moon's gravity, which you could argue is solar energy because the sun's gravity sort of keeps the Earth and the moon all together. Geological upheaval, which comes from nuclear reactions that take place deep within the Earth. Static discharge from lightning. Plants and animals are part of the energy flow on the Earth. And then, of course, the granddaddy of them all is solar energy. And really, the only things that aren't solar energy are these geological upheavals in the tides. And they are a minor fraction. A fraction of 1% of the total energy flows on the Earth. So if you were to say that all the energy flows on the Earth are related to the sun, you would not be far off. You would be 99 point something% right. Another thing I want to bring out this point again. I think we talked about it in one of the earlier lectures, and that's this idea of the sort of difference between matter and energy flows. There are lots of cycles of matter flows, like the carbon cycle, the nitrogen cycle, the phosphorus cycle, ways in which biogeophysical forces, which means plants and animals and minerals and rocks and the Earth's non-living systems work together to continually cycle these materials, because there's conservation of matter. Matter's not created or destroyed, but it's changed from one form to the other. So there are these cycles. Now, you might think there are energy recycling systems on the Earth, but energy is different than matter in that way, and it cannot be recycled because of this idea of the second law of thermodynamics. And actually, to cycle matter, to take matter that's kind of been dispersed and the chemical energy in the bonds has been used up and make it useful again, that takes energy. So the cycles of matter can't happen without a flow of energy. And the flow of energy can't be recycled. In other words, we get a certain amount of energy that comes in and hits the planet. It's high quality, high frequency, beautiful energy from the sun, and that is transformed into low temperature energy, highly disorderly form of energy, and it is then radiated back out into space as low temperature heat, which can no longer do any useful work on the Earth. So the idea here is that in nature, materials cycle, but energy flows. Energy flows from a high quality, low entropy. Low entropy is the idea of kind of concentration or orderliness. So things with a lot of entropy are very dispersed and very sort of disorganized, and things with low amount of entropy are highly ordered and highly concentrated. So it's a little, entropy means disorder in a way. So things flow from high quality, low entropy sources like the sun to low quality, high entropy sinks like empty space. And the idea here is that we can make use of energy as it flows on this inevitable path of energy. We can use it many, many times over and over again until it becomes no longer useful to the system we're looking at because of the second law of thermodynamics. So here's a way to think about, in a very simple way, what life is doing. Really, life is a entropy converter. In a way, it takes solar energy, at a very high temperature, 5,800 degrees Kelvin. Remember, Kelvin's the system of temperature measurement that's based on the absolute zero being zero. And then it hits the Earth and goes through the biosphere at about 280 K, which is probably about 60, 70 degrees. And then it then radiates back out into the universe where the temperature is just a little bit above absolute zero. Remember, 0 K is absolute zero. There's 3 K. So you've got hot photons here. Then they're being sort of the negative entropy or the low entropy. Negative entropy, again, is another word for something that's becoming more orderly, and entropy means being less orderly. So what the biosphere is doing is it's creating order and structure using this high orderly energy from the sun, but it's eventually degrading and being lost as waste heat to the rest of the universe. But in the meantime, we can create a order and structure using that solar energy. So here's another way of looking at that. You have the sun coming in and hitting primary producers of those things on the Earth that can take solar energy directly and make food from it. These are plants and things like that. And then they throw off some waste heat in that process, and that's no longer useful to the system. Then that goes into consumers who get that energy, which was originally from the sun. They get some materials, and then they throw off waste heat. And then this is a primary consumer, so this is something that maybe eats only plants. And then a secondary consumer is something that only eats other animals. And then, again, they throw off heat and they throw off, waste products, things that go into the mineral and matter cycling of the planet. But you see, the energy doesn't really cycle. It comes in, goes out as waste heat, is absorbed and used by another animal, goes out as waste heat. Eventually, all of it goes out as waste heat. So then we've got the decomposers. And so when the primary consumers and the secondary consumers die, some of their energy and the materials are available to these decomposers. And again, the energy goes away in waste heat, but then the materials get cycled through the inorganic material goes to the primary producers, the things, the plants that make, take energy from the sun and create complex chemical bonds that store energy, sugars, starches, things like that. And so this is just, giving you kind of a picture of how life works on Earth from the perspective of cycling of matter and the flow of energy. Here's another version of the same thing that might be a little easier for some people to see, where the sun goes in here, collected by these primary producers, which are the plants. Some of that goes off, most of it actually goes off as waste heat. And then we'll look at exactly how much energy they use. And then you've got heat and materials that go on to the secondary consumers. So these are, it's showing some insects that are eating these leaves. Then those consumers, the decomposers, take those consumers and producers and break those down. These are things like the fungi and other microorganisms. Again, waste. So there's some waste heat there. And again, notice the heat's not cycling, but the materials are cycling back into an inorganic nutrient pool that then goes back to the producers. So this is how the soil food web, these decomposers, take and make everything that plants need through this process, which you'll learn about in the course with Elaine Ingham on the soil food web. Now, we now recognize this kind of primary role that solar energy plays on the planet in creating order and structure and creating the ability to regenerate and renew the effects of entropy. And we talked a little bit earlier about how the sun, 93 million miles away, it doesn't radiate energy just to the Earth. It radiates energy in a sphere that's 93 million miles, a sphere that at the sun's surface, it's about 800,000 miles across. And then it radiates out across the solar system. And that sphere, it's like a balloon. You can think of it like a balloon blowing up, getting bigger and bigger. By the time it reaches the Earth, it's a sphere. And I'll try to kind of show you this, the section of this sphere that's hitting the Earth that's 993 million miles in diameter. And the Earth is just a little speck 8,000 miles across on this big balloon of energy that's 93 million miles across. So it's just getting a tiny fraction of the total solar energy that's emitted by the sun. And another way to think about this is what portion of the sun's surface is actually radiating directly to the Earth, is kind of dedicated to providing that order and structure, that negative entropy on the Earth. And that that's sometimes called the circle of life, and it's only 29 kilometers on a body that is 800,000 miles across. And so you can see we just get a very tiny amount. It amounts to about half a square meter per person that provides all that energy, and that's actually 14,000 times the energy that it takes to run the human economy on the planet. So it's a huge amount of energy, but it actually comes from a very small portion of the sun. And again, we've talked about this before, this idea of the economy of nature, that this box represents the total amount of solar energy that we might get in a year. And if that's the total amount of solar energy that we get in a year, just think about that in your mind as a box of sunlight, all the solar energy for a year. Then this smaller box here is the one that the amount of solar energy that's used to drive the hydrological cycles and evaporation of water and those kinds of things. This is the amount of solar energy that drives the winds that move that energy from the equator up to the poles. And this little box over here is the amount of solar energy that's used to generate all the order and structure for life on the planet through photosynthesis. And there is this little box here is the amount of solar energy of energy that the human economy use, not solar energy, but the total amount of energy. So we get 14,000 times more energy from the sun than we need. And again, we talked before about how these are different amounts of non-renewable energy sources like coal, oil, gas, nuclear. And this is the amount we have forever. Solar energy for a year, coal forever, oil forever. You get the picture. We're already good enough at everything below this line. We just need to concentrate, turn our face toward the sun. So let's take a look at the overall Earth energy balance. So what happens if we look at the amount of solar energy that's, we already talked about the huge quantity of solar energy that is. And I just want to point out at this point that that tremendous gift we get from nature of solar energy to create order and structure has been recognized by traditional cultures all through time. And most traditional cultures have a very special place in their understanding of the universe for the sun and for solar energy. In the Vedic tradition, the sun is considered to be Ram, the ruler of the solar system. And you can see if we're just getting 1/2 billionth of the energy of the sun, it hardly even knows we're here. What's it doing? What's happening in all the rest of the solar system with all that energy? With all that attention that in a way you can think of it as attention that the sun is giving the rest of the solar system, it's just mind-boggling to think. And then there are billions of hundreds of billions of stars, some of them bigger than the sun, all throughout the universe. So you think about the huge, unimaginably powerful radiation of the sun, and it's just kind of mind-boggling to think of the energy flow across the whole universe. So back to the Earth and the Earth's energy budget. If we get 100% of, think of the solar energy coming in and hitting the Earth, as 100% hits the Earth, then what happens to it? Well, 6% is reflected off the atmosphere, 20% is reflected off the clouds, 16% is absorbed by the atmosphere and heats the atmosphere, 3% is absorbed by clouds, 4% is reflected from the Earth's surface, 51% is absorbed by the land and oceans and warms the land and oceans. And then what happens on the other side is it's all reflected back into space. And remember, there's three methods by which heat is transferred: conduction, convection, and radiation. Conduction is things that are directly in contact with each other. Convection is warm fluids rising and falling due to the fact that they're being warmed and they're less dense than the cold fluids around them. So that happens in the atmosphere all the time. But generally, most of the energy that comes from the planet goes back out into space is by direct radiation. It's by direct radiation. And you can see here that 100% of the energy that comes in is actually reflected back out, because energy is not created or destroyed. There's nothing, there's no pocket we can put it in. So it has to flow. And this is where global warming comes in. So what happens is that in order for this, a certain amount of solar energy to come in, the Earth has to be a certain temperature in order for that to reflect back out into the atmosphere. And that temperature is related to the insulating blanket that we have around us, the atmosphere. And if we make that blanket more insulated, then the temperature has to rise higher. It's just like, if you put a down comforter over you, then you lose less heat to the environment around you. So if we put a down comforter over the Earth will get warmer before it radiates all the heat back out into outer space that it needs to radiate. So this is what happens with carbon dioxide gas. Acts almost like a thermal blanket. It's not exactly like that, but it's like extra insulation in the Earth's atmosphere, and it kind of insulation, and it means that the temperature of the Earth has to be higher in order for the incoming solar energy to be able to be radiated back out into space. And again, energy doesn't cycle, it flows, losing usefulness as it goes. Life works to capture and store, to renew and regenerate the useful of energy as it flows. Life is anti-entropic. Life equals sustainability. or sustainability equals life. So here's again oh, excuse me, that's the same. 30% reflected by the cloud surface, 19%. This is just going through this same calculation. And again, what's interesting in this particular slide is that only 0.23% of the incoming solar energy, much less than 1%, is absorbed by plants. And that creates all the order and structure on the planet. So, again, solar energy is just an amazingly abundant source of energy. And you look at the comparison of the Earth's stored energy resources. So if you look at, we've got, let's say, 1 dot worth of crude oil reserves that took 10 to the 8th. That's 10 followed by 8 zeros, which is, I don't know, hundreds of millions of years to create. And then if we look at the latent heat of water vapor, which is when we talked, remember in the talk on energy physics, we talked about phase changes and the fact that when you change from one phase to the other, that a lot of energy is released. So there's a lot of energy stored in water vapor, and when that water vapor condenses to rain, it's released in clouds. And that is the total amount of energy that's stored just in clouds is 2 dots, twice as much as what we have for crude oil reserves, and that's replenished every 10 days, essentially. And then if we just look at the heat content of the top 100 meters of the ocean, that is heated by the sun, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 20 dots worth of energy compared to 1 dot worth of energy for crude oil, and that's replenished roughly every 100 days. So you can just get a feel for, the huge quantity of flow that are used in these systems that kind of regulate the temperature, control the weather. These self-organizing, self-regulating, you can look at them as kind of services that nature provides to us. And we'll talk more about these ecosystem services later in this talk. And so there are other sources of energy on the Earth other than solar, but they're very tiny. There are also certain kinds of organisms that use cycles of that use sources of energy, are able to use sources of energy other than solar energy. They use the heat from vents in the ocean, but they're such a very, very tiny fraction of all of life that it's almost not worth considering. And if you look at, for example, solar energy coming in, it's like 69%. The thermal energy going out is 70%, and there's like 0.025%. There's 0.025% of energy compared to 70% coming from the sun. 0.025% is coming from those nuclear reactions in the Earth's crust, the heat in the Earth's crust. And the tidal motion due to the Earth and the moon, again, that's a factor on the Earth of energy flow, but again, it's such a very, very small amount that 99.9% of close to 99.9% of the energy flows on the sun are related to solar energy, and there's some very minor ones that aren't. Of course, they're important. Things like volcanoes and tectonic plate shifting and earthquakes and all that are related to this energy in the Earth's interior. And of course, we can make great use of tidal power, and tides and currents have tidal currents have a practical use, even though they're very tiny compared to the flow of solar energy. So let's talk about the energy flow in the oceans and the atmosphere. If you look at the Earth is tilted on its axis, and the sun hits the different parts of the Earth more directly. And so typically around the equator, the sun is hitting more directly around the equator. And when it hits up here, the solar energy is spread. It's at an angle, and it's spread over the same amount of solar energy spread over a larger surface of land. And so there's more concentration of solar energy at the equator than there is at the North Pole. So that what that does is that sets up cycles of air circulation. So at the equator, then the warm air starts to rise, and then it it heads north, where at about 30 degrees north it falls and takes the heat that it took from the equator and distributes it there. It cools off and then heads back to the equator, and there's this kind of big cell of circulation of air from 0 degrees to 30. And then from 30 to 60, there's another cell of air on the planet. And then from 60 to almost to the pole, there's another cell. And so what that means is that there's constant wind between 0 and 30, and those are called the trade winds. You might have heard of that. Now at 30 degrees, because that's a place where the air drops back down and then comes back up again, there's a place where there's not very much wind, and that's called the Doldrums, or the horse latitudes. And when people were sailing, they would get stuck there maybe for days until they got in again to the westerlies or the northeast trade winds. And so this is in general how energy gets distributed across the planet from the equator to the poles. Now the Earth is spinning at the same time, so what that does is it sets up a direction to these cells of moving air that are moving the energy from the equator to the poles, and so they actually twist a little bit because of the rotational effect of the Earth rotating. And there you see it. And here again, you can kind of see this. You can see that, in the United States, we have a typical westerly flow. So our weather typically comes from the west to the east. It comes from the west coast and comes across the Midwest and goes to the east. And you can see this kind of overall flow pattern from 30 to 60 degrees on the planet. And then it's been twisted because of the rotational force of the Earth. So you see it heading in this direction. So I wanted to show you, make this flow of wind visible. So let's take a quick look at a couple of websites. So this is a really cool website that shows in real time what's happening with the wind all across the United States. And so what this is showing is that when there's a lot of these white lines, the wind's very fast. This is in the realm of 30 miles per hour. When there are not very many, it's not very fast. And you can kind of see where there are storms maybe, and you can see this place here in the Midwest, which is sometimes called the Saudi Arabia of wind. The annual wind potential here in this area of the Midwest is more than the energy production, oil production capabilities of Saudi Arabia. So we've got to affect our own, energy cartel based on the fact that we've got this really fantastic wind resource through the Midwest. You can see in this case the wind is now flowing kind of this way. It's flowing from the east to the west. And it's kind of interesting to watch. It's not very windy up in New England right now. Quite windy across the Midwest. Now let's take a look at this for the whole planet, which is right here. Oops, sorry. Let me get that. This is a very cool graphic. So this is going to show us in real time what's happening across the whole planet. And it's going to take just a minute to load up. And you can move the model of the Earth around. It's really cool. You can see that there's a big storm here. Off the coast of Europe. This is Spain, France. This is England. You can see, let's see if we can, so you can see, you can turn this around. Let's see what's happening in Hawaii. Whoops. There's Hawaii right there. Let's see what's happening there. Oh, so there's a couple of big storms up north by the kind of Aleutian Islands. It's quite stormy in the North Pacific in the wintertime often. Little tropical storm over here. Looks like maybe heading up this way. Anyway, it's pretty cool to take a look at, what's happening across the whole planet here. Let's look at Asia and Russia. What's happening there? Anyway, you get the idea that this is in real time, and it's pretty interesting to watch. So let's talk about ocean currents. Another way in which excess energy at the poles gets, at the equator gets moved to the poles is through ocean currents. And this is kind of a basic map outline of all the currents all around the world. The red ones are warm currents, and the blue ones are cold currents. You notice that there's a place in the south latitudes down by Antarctica where there's no land all the way around the entire planet. And so the ocean currents can just circulate around the entire planet. And you notice here we've got the warm Gulf Stream, which we'll talk about more in a minute, that comes up along the east coast of the United States. And look, it just plasters Europe with warm water from the South Atlantic and from the equator. And so all of Europe is actually quite a lot warmer than it would otherwise be, because you notice, we'll look at this again in a minute. I'll bring this up again when we have a better map for it. And here's another drawing of what you can see what happens, because not all these currents are at the surface. So the cooler ones, because cooler fluids are more dense and they're heavier and they sink to the bottom, and light fluids like warm water are warm fluids are less dense and they float to the top. So the warm currents float at the top, and then the cool currents go to the bottom. And here is Africa, and so you can see that there are these global circulations of water through again, one of these ways in which everything is connected in all in space and time is through these ocean currents. Now, I was talking earlier about how the Gulf Stream makes Europe, quite a bit warmer than it would be otherwise. Because if you look, for example, at England here, that in Great Britain, that at 50 degrees north, that's further north than almost anybody lives in Canada. Most people in Canada live, right along the border here, and it's far further north than anything in the United States, but it's actually much warmer than any of these kind of areas at the same latitude. In this area of England, southern England, you can grow some kinds of palm trees, and if you look at 40 degrees where Iowa is, that's the latitude of central Spain or southern Italy, where you can grow oranges and things like that. And the reason is because the Gulf Stream brings energy up and keeps it warmer than it would otherwise be. If you've ever seen the movie The Day After Tomorrow, I think that's the name of it, it speculates that maybe one day the Gulf Stream stops and immediately all of Europe goes into the deep freeze. And there's a possibility, actually a scientific possibility of that happening due to the melting glaciers and the melting ice sheets in Greenland that are making the ocean less salty. And there's some speculation that something like that the Gulf Stream could slow or could stop. So here's a picture of the Gulf Stream. Again, here's Europe, here's Africa, Europe, here's Spain, here's the United States, and here's the Gulf Stream coming up here through the Caribbean, along the east coast of the United States, going out and just slamming all of Europe with much warmer weather, even going all the way up into Norway. I think the USDA zone for Norway is around zone 8, and we're zone 5. Zone 8 in the United States is down here. So they can actually grow, figs in some parts of Norway where you can't grow them even in Iowa. So let's talk a little bit more about the Gulf Stream. It was named and mapped by Benjamin Franklin, and he took quite a few trips across the Atlantic, and he noticed that the American sailors could sail to England about 2 weeks quicker than the British sailors, because they had mapped where the Gulf Stream was, and they could stay in the Gulf Stream because they knew it was warmer. They could measure the temperature of it, and so on his various trips across the Atlantic, Benjamin Franklin actually mapped the Gulf Stream, and here's his picture of the map of it. It moves warm water from the equator to the higher latitudes. To give you an idea of the volume of this water, imagine enough heat from the equator to warm all of Europe. 100 million tons of water flow between Florida and the Bahamas every hour, flowing between 2 and 5 miles per hour further northward, and that's warm water. It's bigger than the combined flow of the Mississippi, the Nile, the Congo, the Amazon, the Volga, and the Yangtze rivers. It's actually 20 times greater than the flow of all fresh water into all oceans from the rain, rivers, melting ice, and in other rivers in the world. It has no beginning and it has no end. It makes a loop, as we saw earlier. So it's just continually a flowing stream of water. Now, could we use this to generate energy? Let's hear a NPR story about this, and then we'll talk about it a little bit more.
And in Washington, D.C. recently, Interior Secretary Dirk Kempthorne made an announcement that clears the way to tap an enormous source of renewable energy, the oceans.
For the first time, we will offer regulations to guide the use of wind, wave, and current resources on the 1.8 billion acres of outer continental shelf on the coasts of the Atlantic, Pacific, and Gulf Coast.
In South Florida, researchers are already working to harness the power of the Gulf Stream. From Miami, NPR's Greg Allen reports.
Director Rick Driscoll says the Center of Excellence in Ocean Energy Technology is in a great location. It's just 15 miles from the Gulf Stream.
This is actually the closest location at any place on the planet of a major ocean current. By a load center here that needs the power right now, we've got no place to build power plants, yet we're growing, Florida's growing by 1,000 people a day.
Driscoll's answer, underwater turbines moored in the heart of the Gulf Stream. He believes ultimately the current, which flows at 8 billion gallons per minute, could yield as much energy as several nuclear plants, providing a third of Florida's power. Florida Atlantic University established the center last year for one purpose, to explore ways to tap the ocean's potential as a renewable energy resource. It was started with a $5 million grant from the state of Florida. Inside, the center's offices and workshop area share a common space. Desks and cubicles sit alongside scientific equipment, giant floats, and what, to me, looks like a large propeller.
These are the rotor blades. And
now, is this a large rotor blade? This has got to be, 10 feet across?
Yeah, 3 meters diameter. It's a small rotor blade, very small.
The full-size turbines will be much larger, with rotors 100 feet in diameter. This rotor is for the small prototype Rick Driscoll and his team are building. Pieces of it, the generator, pressure tank, and housing, are laid out on the floor. It's nearly ready for testing. Driscoll eventually envisions a field of turbines moored 1,000 feet below the surface, just off the Florida coast in the heart of the Gulf Stream. There are currently dozens of energy companies, he says, that are developing plans to harness the Gulf Stream. The researchers at the Center of Excellence in Ocean Energy Technology, he says, are studying the best ways to do it and looking for possible negative consequences.
Some of the worst case things we can see is what people have coined the Cuisinart effect, in which the fish will come through and get chopped up, attract, the bait would then attract more fish, and you've got a sustaining Cuisinart effect. Now, we don't think that's going to happen, but it's a possibility and we need to monitor it.
Driscoll says his team is also looking to see what effect the turbines could possibly have on the power and flow of the Gulf Stream. He cites hydrographic data reassuringly to say it looks unlikely to have much of an impact. And even the most optimistic don't hope to extract more than a third of the Gulf Stream's total energy. A few steps outside, welders are working on one of the most massive parts of the Gulf Stream turbine. It's a huge steel buoy that, as project director Gabriel Alcenas points out, is shaped like a ship, so it remains stable in the current.
And what they're doing now is they're adding not only an extra sort of emergency buoyancy, we call them fenders on the side, but also to provide some protection.
The buoy is part of a system tethered to a 30,000-pound anchor that Alcenas says will hold the prototype turbine right in the heart of the Gulf Stream.
The turbine is going to be approximately 30 feet underwater, spinning at approximately 60 revolutions per minute. And this gives us a great exercise in figuring out exactly what effects the ocean's going to have on it, and this is going to have on the ocean and its environment.
Weather and federal regulations permitting, researchers here hope to begin testing their prototype turbine in January or February. If all goes well, they eventually will develop a full-size turbine and maintain an area in the Gulf Stream that will be used as a test field. For Center Director Rick Driscoll, this project is just the beginning of an industry that he believes has great potential not just for Florida, but for the world. Driscoll says his center now is beginning to study an even more powerful potential energy source. It's the large reservoir of cold water deep in the oceans. One obvious use, he says, would be to use the cold water in air conditioning.
but then there's a temperature difference between the warm surface water and the cold deep water, which you can actually use in thermodynamic, thermoelectric, and other processes to generate electricity directly. That ocean thermal resource is probably the largest renewable energy source available anywhere.
Driscoll says by investing in ocean energy technology, Florida will do more than just fill its power needs. It will create jobs and make the state a leader in an emerging industry. Greg Allen, NPR News, Miami.
So if we want to take a look at what those flows look like live, let's take a look at what the Gulf Stream looks like in an animation. It'll take just a minute to load up here. Just be patient for another minute here. Looks like it's coming up. It'll be worth the wait. So you can see what's interesting about this. I apologize for the irritating sound. Is that what's interesting here is when you take a look at what actually happens to the Gulf Stream. It has a lot. It's not like one steady flow. It's actually dispersing out in little eddies all across the. It's just very interesting to see the patterns of flow in the ocean. Cycles of flow off the coast of the south coast of Africa, the continent of Africa. Anyway, that's enough of that. Let's go back to our presentation. And now let's talk about the water cycle. We've talked about this before, about how it connects everything on the earth, past, present, and future, through these big cycles of water being evaporated by the sun, transpired by plants, and then coming back onto the earth as fresh water in a self-organized, self-regulating way that continually renews and regenerates the quality of the water on the planet. This shows here the thousands of cubic meters of water and how it is stored on the planet. So if you look at the oceans have 1,300,000 roughly cubic meters of storage. Evaporated ocean water in the atmosphere is 413 cubic kilometers of storage, and you can see the huge amounts in the relative location. You can see most of the water in the earth is in the oceans. Quite a lot's in ice. Very little actually in rivers and lakes on the land. Quite a lot of it's in the atmosphere. And again, we talked about how that some of the, because of the way that these, that the laws of thermodynamics disperse water across the planet and then concentrate it back in again, that all the molecules of water on the earth have been through all these systems many, many times. And some of the molecules of water in your blood, thermodynamically, you can figure out that they were actually in the blood of dinosaurs, or some of the air, the same things happening to the air. So some of the air you breathe, some of the molecules of air you breathe were once in the breath of Jesus or any other figure that you admire or hate throughout history. You're all connected. And the residence times in the atmosphere, it's about 9 days for the water to cycle through the atmosphere. In the ocean's about 3,000 years for all that water to cycle. And it's been doing it for billions of years. Everything is connected in space and time by these flows. Again, it's one of these, this connectedness we get by going inside and meditating. It's not just a philosophical thing or something that we have inside. It's a physical reality on the planet. And, we with global warming, it's making these weather events more severe. I'm giving this lecture in the fall of 2015. We just had a huge hurricane off the coast of Mexico. It was the most powerful storm ever recorded in the Western Hemisphere. And again, we could look at an interactive map of this, but we won't for right now. And I want to talk about energy flow in the biosphere. So this is the food pyramids and trophic levels and photosynthesis and respiration. So again, this idea that the sun is the high quality energy of the sun is being used by the biosphere before it eventually gets radiated back out and is no longer of use. And the biosphere uses it to create order and structure of life. And one way to think about that is that all the order and structure, all the intelligence we have comes from order and structure that is generated by plants. Their order and structure is coming from the sun. So in some way, in that sense, this Bach sonata that I'm playing, the order and structure of that was forged in the thermonuclear furnace of the sun, creating that order and structure, eventually creating the order and structure of all human thinking and creativity. Now, of course, we know that flows through consciousness, and that consciousness is an element in that flow of intelligence, and how that flow of intelligence becomes intelligent. So let's talk a little bit. This is a really beautiful discovery that somebody made, and what I'm going to talk about now, and this is something that that'll be on your exit exam for the Sustainable Living Program. You'll be asked about this, and this is the relationship between photosynthesis and respiration. So in photosynthesis, what happens is 6 molecules of carbon dioxide get together with 12 molecules of water, and then light comes in, and the miracle of life, plant enzymes come in. And what happens through the process of photosynthesis is the water and that carbon dioxide are recombined to create glucose, which is a complex chemical that has energy stored in it. It has energy from sunlight stored in the bonds, chemical bonds of this glucose. And then it also yields 6 molecules of oxygen and 6 molecules of water. And so plants, through photosynthesis, they take in carbon dioxide and water, and they create and store glucose, which is, again, the foundation of all the order and creativity we see around us in nature, in biology. And then they also give off oxygen, and they also give off water. So in the process of photosynthesis, plants give out oxygen. Now, in respiration, what happens is an animal eats that plant and gets that 1 molecule of glucose, and it also takes in 6 molecules of oxygen, 6 molecules of water, and then what it does is it breaks that down, and when it breaks that complex sugar down, it gets energy out. It gets energy back. So that solar energy that originally went in through photosynthesis is given back to the animal that eats the plant. And what you get out of that is you get energy, which is available to the plant. Now, it took energy to make it up here from the sun, so you're not getting something for nothing. You're using solar energy, so you get energy out of that process, but you also get 6 molecules of carbon dioxide and 12 molecules of water. So animals give off carbon dioxide, and then plants give off oxygen. Now, here's the interesting part. The 6 molecules of carbon dioxide and the 12 molecules of water that a plant needs to do this, they get it. It's completely balanced by what comes out of the animal that eats it. So the animal that eats the glucose, that eats the starch or sugar that the plant made, puts out exactly what the plant needs in addition to light to make that again. So there's a complete connection here, a complete loop between photosynthesis and respiration. And then if you look at what comes out of a plant, which is this complex molecule that has energy in it, this oxygen, this water, that's what goes into the respiration of the animal. So the animal, so it's this beautifully balanced system that runs on solar energy. Again, we don't have to manage it. We don't have to. It's self-organizing, self-regulating. How can we make the systems that we use in the human economy this elegant and this beautiful? So life on Earth is basically broken down into two types: photosynthesizers and those that live on photosynthesizers, that eat them. So the photosynthesizers are called autotrophs, and those that live on the photosynthesizers are called heterotrophs. Don't worry about those words too much, but just to let you know that life on Earth basically breaks down into those two things. Now, there are many different kinds of heterotrophs. There are some that eat plants. There are some that eat other animals. There are some that live off the bodies, dead bodies of animals and plants. And so here's a typical energy budget for a producer. We start with solar energy, an input of solar energy that comes into the plant, and only about 0.8, maybe 1% of the energy is captured by photosynthesis of the amount of solar energy that comes in from the sun. And 45% of that tiny amount that's captured by the leaf supports the growth of that. That's often called the net primary production. It's the biomass that's created. 55% of that is lost to the maintenance activities of the plant or reflected as heat. Now, if something eats that, then 11% enters the consumer food web, and 34% goes to decomposers in the food web as dead material, excrement and waste from the material and the dead bodies of things that die. So you can look at that. That's the kind of basic process, and you can think of it as a pyramid, what's called an entropic. Hold on just a second. It's called a food pyramid, and these are called trophic levels. Hold on. So this is a food pyramid, and you see at the base of it are these 10,000 freshwater shrimp, which actually eat microorganisms that can take sunlight and make starches. So that's where the basic energy comes from. And those 10,000 shrimp feed 1,000 bleak, which feed 100 perch, which feed 10 northern pike, which feed 1 osprey. So this is a food pyramid for a northern lake. And so you can see that the higher you are up on this food chain, the more solar energy. These are called trophic levels. So from the freshwater shrimp to the next level up, the bleak, that's a trophic level. From the bleak to the perch, that's a trophic level. And you notice it's about 10 to 1. There's 10,000 here, there's 1,000 here, there's 100 here, there's 10 here. And that's typically what you find in trophic levels, is that you get about 10% of the energy that comes in is available to the next level. 10% of the energy is available to the next level. So by the time you get up here, it's only, in this, it's a very small fraction of 1% of the 0.001% of the energy that was available here is actually available to that sort of top predator. So let's see. So this is the thermodynamic argument for being a vegetarian. If we can eat these things directly, then there's much more primary productivity from the sun that's available and can feed many more people if they eat here rather than if they eat here. We're making much better use of solar energy. We're making much better use of that flow of solar energy before it's no longer useful to us. So this is the thermodynamic argument for being a vegetarian. And here's another biomass pyramid. Here's the phytoplankton in the ocean, herbivores, which is the zooplankton, then some shrimp, then mid-level carnivores, and then a shark. So you can see 100 kilograms of shark is supported by 1 million kilograms of plankton. Now, if we eat that plankton directly, we'd have to eat a lot fewer sharks. And here's another way of looking at this. You've got solar energy coming in as heat. There's chemical energy stored as photosynthesis. There's energy lost through body activities and heat. Goes into herbivore. The chemical energy goes into the herbivore, and and they get that chemical energy in the food. Then they lose some of it, and you can see that this is the kind of thermodynamic situation. We already talked about 10% law. So in the Arctic, Eskimos hunt whales for food. Whales eat tons and tons of microscopic plankton. This plankton in turn eats microscopic algae. It requires 1,000 units of energy for algae to produce 100 calories of plankton, which is what a whale uses to produce 10 calories of blubber. Finally, these 10 calories of whale blubber contains enough energy to give the Eskimo 1 calorie of energy. So again, you can see from thermodynamic efficiency, it's better to eat lower on the food chain. And this is the energy flow in modern hunter-gatherers, comparing that to how the energy flow in a modern agricultural system. And I think I'm going to skip this. If you want to know more about this, you can come back and look at these slides. I'll put the presentation up. But you'll find that the Bushman food web and the way that it uses energy is much more efficient than the modern agricultural system. So let's do a little exercise here. Take a minute and think about this. One winter, 7 sailors are shipwrecked on a barren Arctic island that has water but neither soil or vegetation. They've got a crate of cornflakes, and a crate containing 7 hens are also saved from the shipwreck. To survive as long as possible, what should the sailors do? Should they kill and eat the hens, then eat the cornflakes? Feed the cornflakes to the hens, then eat the eggs? Or eat the cornflakes and let the hens fend for themselves? So think about that for a minute from a thermodynamic perspective. What's going to give them the most energy? And remember those food pyramids, those trophic levels we just talked about. What do you think? So I don't know what you came up with, but I would go with they should eat the cornflakes and let the hens. They should kill and eat the hens, then eat the cornflakes, because they're going to be the hens are not going to be very efficient with eating the cornflakes, and that's going to it'll take 10 or 15 to 1 cornflakes to get a pound of hen meat that they can eat. And so anyway, that's what I would suggest. But I'm a vegetarian, so I probably wouldn't do that. So I'd probably go with eat the cornflakes and let the hens fend for themselves. So we just have one more section to go through here, and I want to talk a little bit more about energy and ecosystem services. A guy named Bob Costanza. Ecosystem services are these kinds of things that the Earth, that nature does in a kind of self-organizing, self-regulating way, powered by solar energy. Things like the weather system, things like the currents in the ocean. These all provide kind of valuable services for regulating our climate and other things. And a guy named Bob Costanza, an ecological economist, put a value on all those things if we had to buy them. We didn't get them for free from nature. And let's take a look at what that is. So first, ecosystem services, let's talk about what those are. So capital is typically described as assets that are available for use in the production of further assets. So this is kind of a classic definition of capital. And natural capital is the mineral, plant, and animal formations of the Earth's biosphere, when viewed as a means of production of oxygen, water, filtration, erosion prevention, or the provision of other natural services. So these are services we get free from nature. So have you ever considered that the cereal you eat is brought to you each morning by the wind, or that the glass of clear, clean, cold water drawn from your faucet may have been purified for you by a wetland, or perhaps the root system of an entire forest? So all these things are things we get for free from nature. And here's a big list of them. There you can look in this in one of the readings we have from the book Natural Capitalism, and it describes these in a little bit more detail. But there's just a huge range of services that we get really for free. And in many ways, there's absolutely no other way to do them than the way which nature does them. So let's take a look at some of these. Flood control. Much of the Mississippi River Valley's natural flood protection services were destroyed when adjacent wetlands were drained and channels altered for human development. As a result, the 1993 floods on the Mississippi resulted in property damages estimated at $12 billion from the inability of the Mississippi Valley to lessen the impacts of the high volumes of water. So here's a service we used to get, flood control from the Mississippi River. We destroyed that ecosystem service, and it cost us $12 billion as a result. Medicines, 80% of the world's population relies on natural medicinal products. The top 150 drugs used in the U.S., 118 originate from natural sources. So again, these are an ecosystem service, these medicines we get from from plants. Water filtration. This is a really fantastic story. I won't read it. I'll just tell you the story really quickly. But the city of New York needed to expand its water system, and they looked at two different ways they could do that. They could do that by building a machine that would do it, or they could, and that would cost $6 to $8 billion and have $300 million operating expense. Or New York could take $660 million and restore the Catskills watershed. In other words, buy development rights, turn it back into something that could continue to purify the water naturally through the wetlands and through the natural systems that would purify the water in the watershed. And that's what they did. And so they saved many billions of dollars, and the ongoing operating costs. And New York is known for having some of the best city-supplied water on the planet. Pollination, 100,000 different animals pollinate plants. 1/3 of the human food comes from plants pollinated by wild pollinators. So if we had to do this in some other way, it'd probably cost us between $4 and $6 billion per year. So when Bob Costanza added all this up, he came that the services we get for free from nature are worth about $33 trillion. But the whole economy of the entire world, all the human world, is only $25 trillion. So we're actually getting more from nature for free than what we're providing, what was provided for us by the human economy, meaning that we could never replace what we get for free from the human economy, from the nature. And so some other things that the sun does, it provides the gravity that holds the solar system together. In Vedic astrology, it's the king or ruler of the solar system. It provides rhythms and seasons in nature. It's of primary importance for orientation and placement of design elements in environmental design and permaculture. It's on the flag of the global country of world peace. And in partnership with the moon, it provides convenient mood lighting at night. Here's I'm going to close out with these with this last little discussion. So we talked about energy flows in nature, but on the Earth. But the Earth interacts with energy flows from other parts of the universe. Like there's energy flows coming from the sun that interact with the Earth's magnetic field that don't even actually hit the Earth. And so I'm going to just play this little story about that. And you can see this is an actual picture from space about what the northern lights look like. Those high energy particles that come from the sun create the northern lights. So let's just listen to this story.
Thank you for trying Audio Quarter.
The northern lights, or Aurora borealis, are one of nature's most sublime performances. They're pulsating sheets of white and colored light streaming down from the heavens above the North Pole. Auroras appear when surges of charged particles from the sun hit the Earth's magnetic field. The particles emit light, and it turns out they emit sound as well. But unlike the lights, you need special equipment to hear the sound of the aurora. Steve McGreevy has some of that special equipment. He calls himself a natural radio recordist. He travels around in a van recording the sound of natural phenomena. Steve McGreevy invited producer Barrett Golding to turn these sounds of the Aurora borealis into radio. The result is called Sun Song.
This is a whole litany of different natural radio sounds to record. Whistlers and growlers and howlers and tweets. Particles from the sun are hitting Earth's magnetic field and generating these noises probably several thousand miles out in space. It's beautiful. It's primordial. It's Mother Earth singing.
So that's the end of this talk on energy flow in nature, and we're closing with the sound of the earth and the sun interacting with each other at that level of the northern lights.